Welcome back to AI Citizenship for Clinicians. This is the fourth lecture in Module 1. So far, we have introduced AI and how AI can be used in medicine, as well as the potential pitfalls or risks associated with their implementation. Now we will focus on the AI tools that have made the biggest strides and gotten the most press recently, large language models. The goals for today are to introduce the field of natural language processing and large language models as tools, describe why, historically, it has been so hard to utilize computers to work with human languages, and introduce the major steps in the last few years that have enabled AI to use human language in ways that were considered science fiction up until recently. Our perception of intelligence is intimately tied to language. We have discussed many intelligent systems that can learn and make complex inferences that guide actions or output, yet have no ability to actually communicate the processes that they use to external entities. Our conception of true computer intelligence is directly related to its capabilities with human language. This connection between our perception of artificial intelligence as it relates to consciousness and interactions through human language is evident in the many representations of artificial intelligence in media. In fact, the Turing test, which is often discussed as a metric of computer intelligence, was defined as the inability of an outside observer to distinguish a human from a computer system through interaction using human language. The study of how to get computer systems to process and interact with human language is termed natural language processing. It is over 100 years old and spans from Control F in Word through Google search engines all the way to the myriad of uses for large language models we have today. Language models are the engine behind ChatGPT and many other recent chatbots that are powering apps and other generative AI technologies. Language models in their current form have been around for about 8 to 10 years, but up until recently, they have mostly been confined to academic publications and conferences. However, starting with the release of ChatGPT, language models have infiltrated search engines, are powering many of the most downloaded apps, are being integrated into many existing products, and are discussed as potential job disruptors. So what is a language model? Simply put, it is a way of representing the complexities of language in a way that a computer system can understand. More specifically, generative language models like ChatGPT are capable of producing the most likely new sequence of words given an input sequence of words. With small nuances, that's really it. That's all they do. So why have they become so important and ubiquitous? Because it turns out being extremely good at predicting the next sequence of words given a previous sequence of words allows applications across a wide range of settings and functions. Language models have so many applications because communication is central to much of human behavior in society. We are both genetically wired to understand the complexities of language and are immersed in a world full of language from a very early age. This innate ability combined with early and continual training is what makes humans so good at language and their abilities so hard to replicate with computer systems. An interesting experiment that demonstrates both of these concepts was recently completed by a group at NYU. In it, they connected a microphone and camera to a toddler through the ages of 6 to 25 months. Using just 1% of the combined visual and audio data received during this age range, they trained a language model to recognize objects. And while the authors showed that the model could perform noun classification tasks and even some extrapolation across noun meanings, the complexity of semantic and grammatic relationships typically provide much more challenging tasks for computer systems. The ease in which humans learn these relationships is what is thought to be somewhat genetically encoded. Recognizing the advantages humans have in working with language, the task of getting computers to be similarly proficient has been challenging. So why is natural language hard for computers? Language, no matter which language we are talking about, is composed of thousands of symbols that represent both concrete and abstract concepts and relationships. For example, often a distinction is drawn between pictographic versus phonetic languages, but in both cases, the shape of the word element has no easily learned relationship to the meaning, and once learned, this relationship is not governed by rules that are widely generalizable. Next, the same symbol often has many meanings depending on context. For example, go has both synonyms and homonyms, with synonyms not necessarily sharing any of the same shapes, and homonyms not necessarily sharing any of the same meanings. Computers work best with numbers, and while the relationships between these concepts can be represented mathematically, there are significant limitations and challenges. For example, you can represent words in the English language as numbers learned from how each of the words arise in the context of a collection of documents. You can then try to apply simple arithmetic to these numbers to try to understand relationships. One of the most well-known examples of how words can be subdivided into combinations of concepts is the above equation. One can understand how, based on average utilization of these terms across hundreds of documents, a language model may learn that if you take the concept of king, subtract the concept of man, and add the concept of woman, you might result at the concept of queen. However, this result, which again is just the average of hundreds and thousands of examples within the context provided of the model during training, is a vast oversimplification that loses the nuance of how these words may be used, not to mention the multiple additional meanings within less represented contexts. That example translates well to another major challenge, which is that not only is language composed of a large set of arbitrary symbols, but the meaning of each symbol can change over time, and at each point exhibit both redundancy and versatility. As an example, comparing the Oxford English Dictionary now versus 140 years ago, there would be many new additions as well as complete changes in the definitions of the symbols presented within each. Finally, the meaning of symbols are heavily dependent on context, that is, the words around it and the document in which they occur. Therefore, a model learning language for the first time must learn not just what a word means, but how that meaning might change in the infinite different possible combinations of words before and after it. As a salient example, when a document has the term SOB in it, its position in the sentence makes it clear that it is not referring to sob as an act related to crying. Without the example of medical notes in the training data, a human or model may be inclined to think that the writer was insulting the patient. However, if given enough examples of medical notes where SOB was present, the context that this is a history of present illness, or even that the sentence starts with the word patient, may be enough to infer that this is a common abbreviation for shortness of breath. The point is that short and long-range dependencies between words are critically important to understand language, and creating a language model that is good at generating this requires this understanding. As I mentioned, despite all these barriers, researchers in NLP have been working tirelessly trying to understand the best ways to teach computers how to understand natural language. In the pre-personal computer days, this often required coding in specific syntax and grammar rules. Throughout the 1990s and early turn of the century, statistical approaches became more possible through the ability to process more data and encode the statistical relationships between words across larger data sets. However, even with these methods, which allowed machines to learn the meaning of individual words and even the relationships and meanings between words, they still struggled with accuracy in grammar and context flexibility. As neural network approaches became more feasible and more popular in machine learning, a focus on developing language models through ingestion of large amounts of text produced the first large language models. Many of these, including the early series of GPT, could produce human-like text and exhibit some ability to process and understand unstructured text. While this led to dramatic improvements in performance across many tasks, most were still prone to very simple errors in syntax, much less any real capabilities in advanced reasoning or data retrieval. So what has changed? There have been three big changes in NLP over the last few years that have led to exploding capabilities we see today. As usual, many of these changes were driven by money. While the early language models frequently had errors and had limited ability as general-purpose tools without significant downstream training, their ability to generate human-like sentences and conversations allowed people to see the promise in their development. Increased investment allowed everything to get bigger, starting with data. The Olympics is going on right now, so for scale comparison, I took a standard track as the size of the original training set for BERT, which was one of the early large language models. It was trained on about 3.3 billion tokens of data, which is about 8 to 10 million pages of text from a paperback novel. If you stacked that amount of paperbacks along a track, it would be about one time around. As a comparison, estimates of the amount of data used to train GPT-4 is about 5 to 6 trillion tokens, which would be the equivalent of lining up paperback novels from Seattle to Sacramento. The second big change is the scale of the model itself. An agouti is a rodent that looks a bit like a large guinea pig. Though I doubt anyone has tried, exposing this rodent to 3 billion words versus 5 trillion words likely would not change its language ability appreciably. The number of neurons in early language models like GPT-2 versus the most recently trained ones is the difference between the number of neurons in an agouti brain versus 16 independently thinking human brains. Increasing the size of the neural network training on this data allowed for increased storage of information regarding the entities, relationships, and information presented within all the training data given. Finally, a number of technical advances in the last few years have played important roles in the recent increased performance of language models. This includes advances in neural network architectures that allow for more efficient training of very large models, efficient representation of the relationships between words and large sequences by finding ways to allow a model to focus its attention in only the relationships that provide the most information, and techniques that more efficiently train models to exhibit the desired behaviors that fixed some of the challenges old models had that were caused by poor input data quality. In the next lecture, we will get into a bit more of the detail of how the modern LLM is created and how it can be changed and implemented in a healthcare system. For now, we will just say that all of these advances has led to an extremely accurate next word predictor, which is all most current generative AI models are. They take an input and predict what the next most likely word would be. Once they have done that, they add that word to the input and rerun to determine the most likely word to follow the first, and so on. With enough training data and model parameters, next word prediction has led to a language creation that is frequently indistinguishable from human-generated text. For me, this has really made me think about just how much creativity is really in language creation for much of our interactions. Determinism aside, because information transfer is such an important aspect of healthcare decision-making and implementation, current LLM and their language ability can be applied to a number of tasks important for medical care, including knowledge retrieval, summarization, reasoning, and even creativity in decision-making. So where are we now? At this point, LLM can pass standardized tests, write clinical notes that are indistinguishable from physicians, and can transform captured audio into clinical documentation. Many companies are already offering these services and others that will likely change the way we interact with the electronic medical record system, if not change the way we interact with patients. The near future will likely involve combining the power of language models with other modalities important in medicine. For example, can we use language models combined with radiology images to understand features that predict disease in ways that humans haven't even recognized? Or find genetic or family history clues as to the cause for increased side effects experienced and documented by PCPs? Lots of research is being done in the field of trying to combine the different data types within the clinical care to optimize predictions using large language models as a core. In summary, human language is a large, complex set of symbols with inconsistent rules regarding their meaning and relationships. The structure of language makes it inherently difficult for computers to understand. Natural language processing is the field of computer science dedicated to teaching computers how to understand human language. Increases in the scale and recent advances in technique have seemingly overcome these challenges to create language models that have an inbuilt conception of how language works. And these language models have proven very powerful for many downstream tasks.